Hey, welcome back. Let's continue our discussion of optimization. And in this video, we're going to look at a classic example where we're trying to minimize the length of fencing we might need to fence in an area. So we'll call this video optimization example. Minimizing fencing. Okay, so I'm going to write the example that we're going to work in detail, which will take some space here, and that will provide you time if you're taking notes to write the example as well. So we'll start by saying a 216 square meter rectangular turnip patch, 216 square meter rectangular turnip patch is to be enclosed by a fence, and divided into two equal parts using more fencing, running parallel to one of the sides. Okay? And now what we want to do is we want to figure out how to minimize the length of fencing that we need. So one way we could ask that is, what dimensions for the outer rectangle, and we're going to draw pictures of all this soon, but what dimensions for the outer rectangle would require the least length of fence. And then we'll follow up with the second question: how much fence will be needed? Okay? How much fence will be needed? So we're going to kind of walk through this a little bit at a time. We'll set the problem up, draw pictures, and then we'll try to use calculus to solve the optimization problem. Let me turn off my autofocus. I can't figure out how to do that permanently on my phone, so I have to do it in every video, it seems like. All right, so let's draw a picture of this turnip patch. If we were to draw it, we know it's going to be a rectangle. And this is our fence. It's enclosed by a fence, and we want to divide it into two equal parts. So we do that by using more fencing running parallel to one of the sides. The reason they say that is you could cut this in half by running a diagonal as well. So we don't want that. We're either going to think of running fencing halfway vertically down the middle or halfway horizontally down the middle. It doesn't matter which one you put in your picture because we don't know exactly what the fence looks like. So for simplicity, I'll run it vertically through the middle like that. Now, we've got this picture. We have to identify some unknowns. And in this question, we have to identify variables. And in this question, we're asked for the dimensions of the outer rectangle. So we might call this dimension x and this dimension y, okay? So x could be like this width and y could be that length of the rectangle, of the fencing. And then of course, if this length is x, then this length is x and this length is x. And if the top length is y, then the bottom length is also y, okay? Now, we have our variables x and y set up. We've got those defined. We've defined them with a picture. We could use words to describe them and say something like y is the length and x is the width, but I believe this is sufficient to describe what x and y are. The next thing we need to look for in this problem is a known relationship between x and y. So if we look at this, we have to utilize this 216 square meter number somehow. And so that's the area of the entire rectangular turnip patch. And so that could be calculated by multiplying the x dimension by the y dimension, the y measurement. So we know that x times y equals 216. And we'll leave the units off. We'll assume that x and y are both in meters, by the way. So that's good to know. They're both in meters. All right, so what else do we need? We need to look for what we're trying to minimize. So we want to minimize, in this case, we want the dimensions for the outer rectangle that require the least length of fence. So we want to minimize length of the fence. So we'll use L as our function that means length of the fence. So if we look at this picture and we try to figure out how much fence is needed in this picture, we literally just add the 5 lengths. So in other words, x plus x plus x is fence, y plus y is fence. So the length of fence that would be needed for this setup, no matter what x and y are, would be 3x plus 2y, okay? Now, the key to the function that you're trying to minimize is it has to be one variable. And so often what we do to get that is we back up to our known relationship, which is here, and we solve this for one of the variables. So for example, if I want this equation to all be in terms of x, I kind of like x better than y, it's easier for me to write, then I would solve this equation for y in terms of x. I'd try to put everything in terms of x. So I divide by x, and I get 216 over x. Or, because I know I'm going to differentiate my length function, because that's how you find maximum and minimum is through the use of derivatives, it'd be easier if I know I'm going to differentiate this to maybe think of it as 216 times x to the negative first power. And so now we can rewrite our length function as 3x plus 2 times y plus 2 times y, which is 216x to the negative first. And now we've got L as a function in one variable. So let me go ahead and simplify this. So I get 3x plus 432 x to the negative first. And now I need the derivative of this function if I want to minimize this function, try to figure out the minimum, the absolute minimum. So L prime, and this is where it's useful to have it written as x to the negative first as opposed to divided by x, makes it easier to differentiate perhaps. We get 3 minus 432 x to the negative second, okay? And now, if I want to minimize the length function, I need to find the critical numbers from our derivative. So, because I've got this x to the negative second, it's useful to think of this back as a fraction. And we have to figure out where this guy's, the derivative is undefined and where it equals 0. Now, my personal recommendation is to go ahead and get a common denominator and put all this together. So this would be 3x squared over x squared. So I get 3x squared minus 432 all over the common denominator of x squared, okay? So that's one way you can do it. I'm going to erase a bit of this. We've got the original problem here. I will remember the question and we'll come back. Okay, so I've reorganized, I kept our picture, I rewrote the expression for y in terms of x, and I copied L prime. And so now I need to do two things. I need to figure out when L prime is 0. In other words, I need to figure out where the numerator equals 0. So I'll add 432. I'll divide by 3. Let's see, 432 divided by 3 is 144. Oh, this is working out nicely. So x equals plus or minus 12, okay? So those are going to be critical numbers in this problem. The other critical numbers come from the denominator equaling 0. Now, I want to mention something about x and y. We know, since x and y are both links, we know that x has to be greater than 0 and that y has to be greater than 0. Neither one of them could be 0 if we actually have a rectangle. So when I'm looking at this, that's actually going to eliminate 0 as a critical number, and it's also going to eliminate the negative 12 as a critical number. So the only critical number we get is positive 12, okay? Understanding that we're looking at x values bigger than 0. So now if I want to find the absolute minimum of our length function, let's see, what was our length function again here? I forgot to copy that down. 3x plus 2 times, so 412 times x to the negative first is our length function. Okay? Or we could even, 3x plus 2y, we'll just call it that. Just so I've got y, I've got my length, and I've got my derivative. Okay, sorry about that. Forgot to write down my length function. Okay, if I want to find the absolute minimum of this length function, I found my critical numbers, and I'm going to look at my chart with x, L prime, and L. I'm going to use what I know about L prime to tell me when L is increasing or decreasing to try to determine absolute minimum or maximum. The only critical number I have is when x is 12. So over here, I'll be looking at x values bigger than 0 and less than 12. And over here, I'll look at x values bigger than 12. And by the way, x could be any big number because if I make x really big, then y just gets smaller to keep my area equal to that 216 number, okay? All right, so we already know that if x is 12, L prime was 0. It made the numerator 0. And if you look at x values less than 12, maybe like 10, and plug them in here, you'll see that this whole L prime expression is negative. And if you look at x values bigger than 12, L prime turns into positive. So if L prime is negative, we know that L, the original function, is decreasing. If L prime is 0, we have a horizontal tangent line of the original function. And if L prime is positive, we know the original function is increasing. Okay? So if our function is continuous, which this function is continuous, everywhere past 0, so there's nothing weird that happens past 0, and it's decreasing until it hits this horizontal tangent line and then starts increasing again, this has to be our absolute minimum at x equals 12, okay? So we know that x equals 12, and the question asks for the dimensions of the outer rectangle. Well, x is one of those dimensions, so that's good. And we know that it's measured in meters. But we still need to know the dimension for y. So if x is 12, how do we get y? Well, we go back to the original known relationship between x and y, which remember said x times y equals 216. And that's where we got this y equals 216 divided by x. So if I divide 216 by 12, I get 18. So y is 216 divided by 12, which is 18. So the answer to the first question is 12 meters by 18 meters will require the least amount of fencing, okay, in this scenario, and it will keep our area to that 216 square meters. Now, the second part of the question is, how much fencing do you need? Well, now we can come back to our drawing and we know that each of the x's is equal to 12 meters and each of the y's is equal to 18 meters. So we can add those all together. We get 36 plus another 36. So the second answer is 72 meters of fencing. So that's the least amount of fencing you would need to purchase if you wanted to build a fence like this to enclose 216 square meters for your turnip patch.